Hello everyone, I'm 海滨史. My colleague Yongke Wang and I will give a talk about Android Chrome. Shared with hope, new security mitigation helps us escape Chrome Sandbox to exfiltrate user privacy. Let's begin. We are from Tencent Company, the largest social media and entertainment company in China. And my department, Tencent Security 玄武 Lab, is a security research lab based in Beijing. We focus on various applied and real-world security research. Yongke Wang and I are members of mobile security team of our lab, mainly focused on Android bug hunting. This is outline of our work. We will introduce the work from following 5 parts. First, we will show a brief introduction about Chrome security mechanism. This is an evolution of browser process architecture. Before 2007, all the browsers are single process. Since 2008, Chrome became the first multi-process browser. And now, the architecture of Chrome has changed a little. For example, the network process are out of browser process now. Now, take a look at basic security policy of Chrome. Same arrange policy. A basic security policy of Chrome protect the web resource from different arrays. And cross-array resource sharing, and no other course, can relax the restriction of same array policy slightly. It means some cross-array requests can be allowed. There are some special protocols on Android, such as content. Through content protocol, we can access media files on Android by media or download provider. How about cross policy between content, HTTP or HTTPS, and file protocol on Android Chrome? There is a case about content protocol on Android Chrome. Judge and Robert performed an attack chain on Chrome in 2017. Their attack chain contains 3 steps. First, download the payload. Then jump to the content domain from HTTP domain. Finally, read other resource using content protocol. At that time, course chink about content is very weak. After that chain, Chrome do some fix. Now, the payload, which downloaded in step 1, will be renamed to MHT, and the JavaScript code will be removed. The jump in step 2 will be intercepted, and the cross-domain access in step 3 is also blocked. So the fortune is broken completely. But during our research, we found that the restriction in step 3 disappear after an update of Chrome. What happened? Why the course between content domain failed since version 79? This is due to a change of course implementation named OR course. Let's learn more about it. OR course is a new course implementation introduced to solve some historical design problem and to be more secure. Before this change, Chrome implement course in the render engine, Blink, running in a render process. OR course means course will be moved to network service, running in a separate process. Let's look at it in Chrome Android. Before version 79, OR calls are not completely done. But we can turn on a switch named Auto Blink calls to experience this feature ahead of time. In version 79, OR calls are undone, and the switch disappears. But actually, some calls check are not moved to network service completely. Show me your code. The code shows enforcing about resource request from render process to browser or network process. If Auto Blink calls enabled, enforcing in make cross bridge access request will be removed. This code shows the enforcing about resource response to render. If Auto Blink calls enabled, we will escape from the following enforcing again. Unfortunately, two checks mentioned before are not moved to network service. The check turn off in render doesn't appear in network service. This leaves a hole in OR calls. It means before Auto Blink calls enable, the request between content domain will be blocked because of the course chink in render process. But with OR calls enabled, the chink of content request disappear completely. So content can cross-domain access other content without any check. This is a code example to read media file by Ajax request. And we can set the file content to our server. The hole also exists in Android Web View. We can trigger this bug as long as set allow content access enabled. without set allow field access from field users or set allow universal access from field users enabled. In short, our course is introduced in Chrome for Android as a security mitigation. But we found a bug in the mitigation mirror, just like a hole in the shield. Now, let my colleague Yongke Wang show you the following part. Thank you.
Hello everyone, I'm Yongke Wang. My colleague Haibin showed the hole we found in Chrome. Let's go on. Now we have a cross-domain access bug, but it's not enough for us. We want a bug chain to attack Chrome for Android remotely. So let's begin to detail our full exploit chain. In step 1, we should download HTML payload file to external storage automatically. And we tried many ways with HIF and download attribute of the HTML A tag, and simulated click the A tag by JavaScript. And we found that in this way, Chrome will open a .html file directly. So this way is not okay for us. The second way, Chrome will download mhtml file, removing JavaScript code from the original HTML file. So this way also fails. The third way is the same as the second way, so it also fails. And the last way, Chrome will download a .html file to the download directory of external shared storage, which metatype is text/html. So this way works well for us. At last, we found a way to download HTML payload file without any user click. So step 1 is done. In step 2, we try to jump to content from HTTP or HTTPS. And this is the test result of cross-domain jumping between HTTP, file, and content. After Jody and Robert's work, content has become a local scale, the same as file. So we cannot jump to content from HTTP directly anymore. When we look into the Android manifest file of Chrome for Android, we found the intent dispatcher activity. This activity can accept a deep link from browser with content at data scale, text/HTML at date metatype. So can we jump to content by deep link? According to the intent filter of intent dispatcher activity, we can deduce the intent object that should send to this activity. The intent object should look like this, which action is android.intent.action.view. Category is android.intent.category.browser. Data is content, :// blah blah. Main type is text/HTML. So what deep link can be passed to this type of intent object? In the light of Android app deep link pattern, we can get the result deep link like this. So we get the deep link, but which content provider should we use? At last, we found the Chrome file provider in the Android manifest file. And Chrome file provider extends file provider of Android framework. File provider will transform content URI to file path by the rule defined in the XML file passes. This is the root file for Android Chrome, located in res/xml/file and line passes.xml file of Chrome APK. And the external path represents the external storage path. Usually the result of environment.getExternalStorage directory API. And the cat path represents the private cache directory of Android Chrome app. For example, the above content URI on content provider level will be mapped to this file path on file level. And this is the mapping for cache passwords. When users export their saved website password from Chrome, user account name and password will be saved in this type of file in plain text. So, step 2 seems done by this Android app deep link. But during our research, Android Q jumps out. And one security mitigation called scoped storage broke our step 2 on Android 10. What is scoped storage? It is an security mitigation on Android shared storage inspired by Sandbox. And apps are limited to only access shared files they own and cannot access shared storage directly, for example, by file API. Apps only can do it by media provider app. If we try to jump to content by this deep link, Chrome shows that file not found. The reason is that Chrome file provider uses file API to read the payload file, which is forbidden on Android 10. So this deep link does not work anymore on Android 10. How to bypass scope storage? We can use this content URI. Chrome requests to media provider by this content URI. Then media provider returns a parser file descriptor of the requested file back to Chrome. because the payload file is downloaded by Chrome itself. So the enforcing from media provider is alright. But another problem comes out. We cannot predict the ID of the downloaded payload file. And this way, by script element to probe ID is not working anymore, because we cannot access content under HTTP. Inspired by heap spray in binary heap exploit technology, we came up with an idea: file spray. We can download multiple payload files to improve success rate. As long as we hit one of the downloaded payload files, we can jump successfully. But Chrome blocked us if we try to download multiple files in the same tab. Like the picture shows. Come back to the Android file of Chrome for Android. We found that we can jump to HTTP by deep link, just like jumping to content. By this deep link, Chrome will open this HTTP URL in a new tab. So, first, we download one payload file automatically. Then, jump back to text.html itself by this deep link. We can download multiple payload files without any blocking. After download multiple payload files, we can jump to content by this deep link, with assigning one number to ID. So, step 2 works again. When Android 11 comes out, it allows us to use File API to access shared storage again. So, these two deep links are all okay on Android 11. Good news or bad news, we don't know. By exploiting the hole of shield in Chrome that my colleague Haibin showed before, step 3 is okay already for us. Job seems done already. But the update of Chrome 83 broke our exploit chain again. Jumping to content from HTTP in step 2 was blocked. We must find another way to bypass the blocking. What happened? We dive into the deep link parsing code of Android Chrome. Chrome will call intent.parseURI function to pass deep link to intent object firstly. Then do some filter on the intent. At last, we found two checking points in should override URL loading internal function. These two checking will filter intent containing file on content scale. So Chrome will block the deep link that jumps to file or content. So the current situation is like this. Everything is okay except for Chrome 83. Jumping to content by deep link is blocked by Chrome itself. Can we do it by deep link out of Chrome? Of course, we can trigger the deep link from Samsung browser app. But the exploit chain is not perfect. Depending on other app. Can we do it only by the pre-installed apps on Pixel devices? Maybe jump to one app from Chrome, then jump back. Just like ping pong. So, if we can jump to another app by deeplinking A from Chrome, then jump back by deeplinking B like this, then we can finish step 2. So, what is the deep link A? After a lot of searching, we target Google Quick Search Box app because we found that it can accept intent with Android app scheme as data URI. After reverse analyzing the Google Quick Search Box, we found that it accepts Android app data URI from deep link. Then pass the data URI by intent.parseURI function. So we can get the deep link A like this. First, we can trigger the deep link A in Chrome. It will send deep link B to Google Quick Search Box app. Then Google Quick Search Box app passes deep link B, jumping back to Chrome. We call this type of attack deep link reflection attack. By now, job is really done. Let's take a look at our demo. First, demo 1, attacking Chrome on Android 10. We use two devices. The left one is Pixel 4 as victim, and the right one is as attacker. First, let's look at the Android system version. It's Android 10 and is already up to date at that time. Then look at the version of Android Chrome. It's 83 and also up to date. We prepared a picture in the left victim device in advance, and this picture does not exist on the right device. Then we send one short message with a link to the victim. After the victim clicks the link, our exploit begins. Our exploit downloads multiple files at first, then jump to one of the downloaded payload file by content scan. Exfiltrate the picture and send it to our server. On the right side, we can download the picture from the server. Then we got the picture. It's the same as the picture on the left device. Okay, this is the end of our demo 1. Let's look at our demo 2, attacking Android web view on Android 10. We take an app called Wish as an example. Just like demo 1, the version of Android system is up to date. Let's look at it. It's also Android 10. Then look at the version of Android web view. Then look at the version of Android Chrome. It's 83. Look at the version of Wish app. It's also up to date. We also prepared one picture on the left device, and the picture does not exist on the right device. Then we send a short message from the right. Once victim clicked the link, our exploit was triggered. At first, download multiple payload HTML files. Then jump to Wish app by deep link, loading payload HTML file by content scan. Then we can get the picture on the right device. It's the same with the picture on the left. Okay, it's the end of our demo 2. Let's go on. How are the bugs fixed? For bug 1, Chrome's security team won't fix it. Bug 2, Chrome opens HTTP URL in the same time, so multiple files downloading can be blocked. Bug 3, the browser category is removed from the intent filter of intent dispatcher activity. So we cannot jump to content by deep link. Bug 4, cross-checking on content is enforced out of render process, just like file. Some takeaways: be careful when introduce security mitigation. It may be introduce bugs. We explain the reason why new security mitigation leads to vulnerabilities. We also detail some skills to bypass all kinds of mitigation in our exploit developing process. And the last one, the security of Chrome is also influenced by surroundings besides itself. For example, In our deep link reflection attack, we can attack Chrome by Google Quick Search Box app. Thanks for the great work of Georgie and Robert. Their previous work helped us a lot. Thanks to Chrome security team members. They respond quickly for our bugs we found. And at last, thanks to our team members from Tencent Security Xuanwu Lab. They gave a lot of help to us during our research. Okay, our talk is over. Thank you.